All right, all right, all right. Morning. For those of you that don't know, that's I'm channeling my inner Matthew McConaughey from Dazed and Confused. Not Matthew McConaughey from Magic Mike. Not going there. But Dazed and Confused is all right. So we're going to really make an attempt to finish up on chapter, I guess it's 8, our periodic march through the main group elements, because we're already a little bit behind what the syllabus says, and we don't have days to spare. So we're going to try and power through. We'll see how we do today. Last time we finished up on this concept of the inert pair effect. We spent a little bit of time talking about it and postulating reasons that the heavier elements of the carbon group might not want to give up their NS electrons, the NS2 configuration, exemplified most prominently by this last reaction where solid lead will react with chlorine gas, but only to give the lead 2 dichloride, okay, which is a stable compound. You cannot use chlorine to oxidize it up to the lead 4. And again, if we thought about this kind of from first principles or what we were taught in freshman chemistry, it would come as a surprise. First of all, you can't isolate carbon dichloride, right? Doesn't exist. It's too unstable. Goes right to carbon tetrachloride. And what we usually think is it's easier to reach higher oxidation states with heavier elements because the valence electrons are further away from the nucleus. They're not held as tightly. And so this is a perfect example of one of those trends that nobody really expected on the periodic table until we went out and did the experiment. Then we had to go back and try and come up with a plausible explanation as to why it occurs. Okay, and so you always want to be thinking about these things and realizing that as good as you have your freshman chemistry principles down, sometimes you're going to be thrown a curveball when you actually go and do an experiment. So the heavier elements of the carbon group also show a diverse set of different structures and even electron counts. So you can see in the top left corner we can get trigonal planar silicon. Okay, that probably isn't a surprise because we know we can get trigonal planar carbon. We of course can get tetrahedral. So there's one for you. Even though you can't oxidize lead to lead tetrachloride with chlorine gas, you can make tetramethyl lead. Okay? We used to use tetraethyl lead all the time, right? You ever wonder why we have unleaded gasoline? Well, it's because back in the day when your parents were kids, we used to put tetraethyl lead into the gasoline because it would keep the engines from knocking. It was a lubricant. Can't do that anymore because lead's bad for you. We can get 5-coordinate, so there's tin pentachloride anion. Okay, so right now we've achieved a geometry that you don't see with carbon. You can get this odd-looking square pyramidal geometry with silicon, another anion. In the case of germanium, if you take germanium tetrachloride and put it in pyridine, you'll coordinate 2 pyridine molecules and make an octahedral 6-coordinate compound. Okay, again, now what this slide is illustrating is something, again, you probably learned in freshman chemistry. When you get to the heavier p-block elements, you can expand the octet. So the octet rule is pretty much a hard and fast rule for the 2p elements, right? You never violate it for carbon. As you get to the heavier p-block elements, you violate it all the time. And we say that this can happen by using d orbitals and getting to some fancier hybridizations, which has some validity. Now, the other interesting thing about these heavy carbon block elements is how in another way they differ from carbon is in multiple bonding. Okay, we mentioned last time that one of the things that makes carbon cool as a building block is you can get carbon-carbon single bonds, double bonds, triple bonds. We know from Chem 51 that multiple bonding leads to reactivity. A lot of times that's what we exploit when we're building bigger molecules. Turns out that when you drop down the periodic table, multiple bonding is different. Okay, and so Here's a kind of nifty reaction where you have this silocycle butane. If you heat it up to 560 degrees Celsius, you can do a retro 2+2 addition and expel out ethylene, okay? And in theory, that should then generate a silylene, or a silicon-carbon double bond. The problem is this species is incredibly unstable, and it basically immediately polymerizes to make a silopolymer. Really is just kind of goo in the bottom of the flask. Now, if you really want to isolate multiple bonds with silicon, you have to kind of go to great lengths, okay? And so if you take silicon and you put two mesotyl groups on it, and you make the trimethylsilyl. So this is a silicon-4 compound, tetrahedral, not too terribly surprising, except that you have these bulky substituents. If you irradiate this with UV light, you can blow off those trimethylsilyl groups and generate the silicon equivalent of a carbene. That silicon equivalent of the carbene can then dimerize and form the silicon-silicon bond, double bond in this case. But what you find when you get the crystal structure of this compound is that the silicons are not sp2 hybridized. Okay, that's what we would expect for carbon, right? That each silicon would be perfectly planar and it would be sp2 hybridized to form the pi bond. In this case, I've drawn it with the full double bond, but those silicons are very pyramidalized, which makes it look like there's almost a lone pair or a single electron pointing out in an orbital. So it almost looks like the silicon is partway between sp2 and sp3 hybridized, and as such it has a very weak silicon-silicon double bond. You could put that in air quotes. In fact, you'll have free rotation around the silicon-silicon bond. It's so weak. Now that's kind of conventional double bonding, what we think of the carbon does very well. It turns out that the heavier elements will participate in multiple bonding, but in kind of a masked way or in an unusual way. And we can see it in kind of the tertiary amines. So we all know that trimethylamine, we've probably talked more about trimethylamine in the last couple of weeks of class through our acid-base chapter than you ever thought we would. We know that trimethylamine is a pyramidalized compound. It's got a lone pair on the nitrogen that sticks up. That's the Lewis basic. You know, we can all do our VSEPR type arguments and tell you what the shape is going to be. That bond angle is a little bit larger than it is in a tetrahedron, 112 degrees. But the nitrogen is definitely sp3 hybridized with that lone pair. If we compare that to the silicon analog, so instead of CH3 groups on the nitrogens, we have the SiH3 group. We find that that molecule is planar, which is a little bit odd because that suggests now that the nitrogen is not sp3 hybridized, right? It suggests that the nitrogen is instead sp2 hybridized and that that lone pair is now in a regular pz type orbital. And sure enough, that's exactly what we think is going on. Similar things happen in silanols, the silicon equivalents of ethers. The oxygen-oxygen bond or the silicon-oxygen-silicon bond opens up. And the way that we rationalize this is the same way that we rationalize heavier elements expanding their octet. We invoke the use of the d orbitals on the silicon or the heavier carbon block elements. And so if you take this, what we'll call the d YZ orbital on silicon, it's empty, put it next to a PZ orbital on nitrogen, you can see how you can generate kind of a dative bond where the lone pair on the nitrogen atom could donate into that empty orbital in silicon. Okay, a dative bond is a type of covalent bond. It's a polarized covalent bond. Represents the donation of a pair of electrons from a neutral Lewis base to another acid. But what that interaction does, that you can call it p-pi d-pi bonding, is it keeps the nitrogen sp2 hybridized so that you can get overlap both above and below the plane of the nitrogen-silicon single bond. Now, as you might expect, this effect is pretty good for silicon. As you drop down the periodic table in the carbon group, it becomes weaker. It becomes weaker because the orbitals are a lot bigger on the heavier elements. Okay? As you drop down to 4d orbitals and 5d orbitals, the overlap between those orbitals and the nitrogen 2p is weaker. Okay? The smaller overlap means a weaker bond, means the multiple bond character is not as good. Okay, so that finishes up the carbon group for us. And so we keep with our periodic march and we move over to nitrogen. So again, I've already mentioned this. We talked about the Haber-Bosch process briefly in the lecture on hydrogen. It is probably the biggest industrial use of hydrogen is to convert nitrogen to ammonia. It's the reason that we all can eat as well as we do. Turns out that that's also pretty much the fundamental reaction for all nitrogen chemistry on an industrial scale. If we take ammonia, we can react it with methane. That seems like kind of an interesting reaction, right? How do you react methane and ammonia? They seem like two molecules that shouldn't react. Turns out I've left out the oxygen that's usually in that reaction, and you can make everybody's favorite murderous gas, hydrogen cyanide, in that way. The reaction is driven by the formation of water when you have O2 present in the reaction. It's carried out at like 1,000 degrees with a platinum catalyst. Another really, really pleasant reaction is the reaction of ammonia with phosgene. Phosgene was, of course, a chemical warfare agent back in World War I, so you probably don't want to live next door to a chemical plant that's preparing urea, even though urea is common fertilizer. That's the basic building block. We typically take a lot of our ammonia, react it with phosgene to make the urea, which is a really good fertilizer for easier to use than ammonia for sure. I think it's probably no mystery that if you react ammonia with acids, you can generate various ammonium chloride salts. And if you take ammonia, react it with O2 in the presence of water, that's how you generate nitric acid and the nitrate anion, which is, again, a very useful, very important industrial chemical. We can see why we do this by looking at the thermodynamics. So if we take ammonia and we react it with oxygen, we generate water and 4 equivalents of the nitrite of NO2 aqueous. That reaction's downhill by 97 kilocalories per mole. Very favorable reaction. We can then take that and basically hydrate it. You can imagine if you have it in water, it's basically hydrating itself to make nitric acid and NO, which we'll talk about in a minute. Again, a favorable reaction downhill by 1.2 kilocalories per mole. Now, you might be saying, well, wait a second. Why am I taking nitrogen, going through the Haber-Bosch process, reducing it with hydrogen to make ammonia, then taking that ammonia and basically burning it in oxygen to make nitrogen oxides? It seems that you should just be able to take nitrogen and react it with O2 directly to make nitrogen oxides. Well, it turns out that you can't. And so if you try and take nitrogen and oxygen to make NO2 in the gas phase, that reaction is uphill by 12 kilocalories per mole. And so part of that, at least, is going to be entropy, right? We can look at it immediately. We're starting with 3 moles of gas. We're going to 2 moles of gas. That's going to be entropically disfavored. So that means the higher you heat the reaction, the less it's going to want to go to products. But then you also have the issues with the enthalpy of the reaction. And again, we can just look at this in a qualitative way. We know oxygen's very reactive. It'll react with lots of different things. We'll talk about that later today. But nitrogen's got a triple bond. It's one of the strongest bonds that we know. Okay, and so you're basically exchanging that nitrogen-nitrogen triple bond for nitrogen-oxygen double bond type things with resonance structures and whatnot, okay? It just doesn't really want to go forward. Now, these nitrogen oxides, again, important chemicals, at least if you care about the air that you breathe, okay? So the brown layer that we often see over LA, a lot of that brown comes from nitrogen oxides, NOx's, okay? And so these are the baddies that come out of the exhaust pipe if you are not burning clean fossil fuels. Right? We all know that if all you have in your gas tank is hydrocarbons, right, and you're burning it in pure oxygen, all you're going to get out is CO2 and water. But when you have other crud in there, I mean, let's think about how we do this, okay? We've got to, we put a pipe in the ground and we just pump out whatever's kind of liquid and distill it. And you've all done distillations, right? Sometimes it works really well, sometimes it doesn't work so well, and other stuff comes through. If you have heterocycles like pyridine, a little bit of pyridine that gets into your gasoline, well, now when you burn it, you get nitrogen oxides, bad things. So one of the common ones, I don't know about you guys, I actually ended up studying this reaction when I was in P-Chem lab as an undergrad, because you have this really ugly brown gas. And based on the absorbance of the brown gas, you can calculate the equilibrium constant. And so, we did really fun things like change the overall pressure and calculate where the equilibrium is and how much N2O4 and how much NO2 we have. Turns out the equilibrium constant is about 0.115, okay, which immediately tells us that the reaction lies to which side? Yeah, right, it lies to reactants. Which, okay, if you have a flask that's filled with pure NO2, it's going to dimerize and go back to the N2O4. If you're talking about it as a minor component in the atmosphere, okay, concentrations much less than 1 atmosphere of the NO2, well, then you're going to actually move over to the right-hand side. And believe me, you don't want to be breathing in that awful NO2 gas. You don't want to breathe in N2O4 either. The NO2 has further reactivity in water. It'll actually disproportionate. And so you can take the NO2 anion, it'll react with hydroxide, and you can generate NO3. What did I do here? Something is a mess. Oh no, it's all okay. Forgot I was bringing in the negative charges with the hydroxide anion. And in aqueous solution, that NO2 anion will react with acids to make the NO plus cation plus water, or you can add 2 protons and an electron to generate neutral NO gas, and again, the byproduct water. So NO, since you guys are all chemistry majors, and I know you're just as big of chemistry dorks as I am, NO was actually named Molecule of the Year in 1992. Right? I'll bet you didn't even know there was such a thing, right? So yes, you can be Molecule of the Year. I don't know if you get a plaque that goes on your mom hangs on the fridge or what, but it was also responsible for the Nobel Prize in Medicine in 1998 because it turns out that NO, which is a pretty simple molecule, it doesn't have a high atmospheric concentration, has a lot of biological signaling roles. Turns out that that small molecule is responsible for a lot of the neurological signaling that goes on in our bodies. And so neurotransmission, neuron-to-neuron signaling, it's a vasodilator, and it's known to relax smooth muscle tissue. It turns out that was a big part of the Nobel Prize, and it was actually the understanding of this biological signaling pathway. And so I'm not a biologist, so I have to look at my notes here to get these names right. So it turns out that NO, right here in yellow, binds to guanylate cyclase receptors. So that's that in the blue box across the top. And when it does, what that does is it results in the production of this, where is it? This GMP right here. And you can see that this has a cascade effect that results in smooth muscle, the relaxation of smooth muscle fibers, vasodilation. Okay? Now the problem is right here, this PDE. Okay? PDE is a phosphodiesterase, and that one has the specific duty of breaking down the GMP protein, which results in smooth muscle relaxation. Now, why do you care? Well, it turns out that the heart muscle is all smooth muscle tissue. So smooth muscle tissue is muscle that works without basically our thought, okay? It just is expected to go and go and go and go. And so Pfizer came up with this drug that was basically would come in and bind to the phosphodiesterase, basically blocking it from coming in and decomposing the GMP. The idea is you would administer this drug to old men having a heart attack, and it would basically relax the smooth muscle tissue so blood would flow and everything would be okay. Didn't work. I mean, it sort of worked, but not really. Not well enough that it could actually be used as a heart treatment. But this is one of those cases where sometimes life gives you lemonade when you have lemons. Turns out that heart muscle tissue is not the only smooth muscle tissue, and the same candidates that have heart attacks also have other issues. So it's a, really, really successful drug for Pfizer. Chemistry is great. Okay, so those are the oxides of nitrogen. What about some of the lower valent nitrogen compounds? So again, here's nitrous oxide. Two important uses. One is as laughing gas. Another is as basically rocket fuel for your race car. Okay, so if you ever hear about people drag racing and having nitrous, there you go. You inject it into your engine in very small doses at the right amount of time. You get a massive increase in horsepower. You don't just pour it in because then your engine explodes. I want to use this as a time to remind you of some of our formalisms when it comes to electron counting. This is going to become really important and potentially confusing as we go forward with the transition metals. So I'll remind you that we have two different types of electron counting that seem similar. One is formal charge. Okay? When we do formal charges on atoms, we take the electrons in any bond and we split them. Okay? For a single bond between two atoms, one electron goes to the atom on the right, one electron goes to the atom on the left. It's always split. You split every bond evenly. You can contrast that with the oxidation state. Okay? And for the oxidation state, the electrons get assigned to whichever element is more electronegative. Okay, typically when we're talking about main group, we spend more time talking about formal charges than we do oxidation state. Okay, that's why we put, in this case I have formal charges labeled on the nitrous oxide. But we can also go in and put in oxidation states. Okay, and so in this case we see that there's some correlation between oxidation state and formal charge, in that we could say the middle nitrogen has both a higher formal charge and a higher oxidation state than the nitrogen on the left, but there's still not really a one-to-one correlation. We can look at things like azides. Okay? Azides are sometimes viewed as pseudohalogens because it's an overall 1- anion. And so in this case, you can see that there's a high degree of correlation between the formal charge and the oxidation state. I will point out that your oxidation, if this is a good example, if you sum up all of the oxidation states, it has to equal the overall charge on the fragment that you're looking at. Okay, so the azide ion is a 1 minus anion. And so if you sum up either the formal charges or the oxidation states, you better end up with 1 minus. If you're doing a neutral compound, when you sum up the formal charges or the oxidation states, you better come up with the correct charge on the overall neutral fragment. Diazine, here's an example where the nitrogens have both formal charges of 0, but the formal oxidation state is -1 because both of the electrons in the NH bond get assigned to the nitrogen. For oxidation states, when you have two of the same element, like the nitrogen-nitrogen double bond, in that case you split the electrons evenly. Hydrazine, effectively what we're doing here is we're reducing diazine, we're hydrogenating it. Okay, that's a reduction in organic chemistry. It's a reduction here in this nitrogen chemistry as well. And the oxidation state of the nitrogen atoms drops from -1 to -2. Now you might imagine that's fairly reduced nitrogen. Okay, and as such, hydrazine acts as a reducing agent itself. It pretty readily will give up all 4 of its protons and 4 electrons, and what do you know, it spits out N2, which of course is a pretty stable molecule. So really, hydrazine is a 4 electron, 4 proton reducing agent. Diazine can also act as a reducing agent, but it's not nearly as potent because the nitrogens are in a lower formal oxidation state. Well, technically a higher formal oxidation state, but we're talking absolute values here. Okay. The heavier congeners. So phosphorus, astatine, bismuth, all through here. As we move down, as you might expect, the same trends that we saw in the heavier elements of the carbon group hold for the nitrogen group as well. So we can take P4, which is the one elemental form of phosphorus, react it with chlorine gas, get an initial oxidation up to PCl3. Okay, so this would be a trigonal pyramidal. It's a liquid, very, very water reactive, pretty noxious. If we take that and react it with chlorine further, we can generate PCl5, which is still water reactive, but it's also a pretty potent oxidant. And then if you take that species and react it with chloride anion, you can generate PCl6, which is now octahedral phosphorus. Again, we're exceeding the octet rule, but that comes as no surprise. If we drop down all the way to bismuth, the heaviest of the nitrogen group, well, I guess by that time it's a metal, you can't get past bismuth trihalide, and that again is because you just cannot oxidize off that lone pair, the S2 electron configuration from the bismuth center. Now it turns out in inorganic chemistry, inorganic chemists in general love phosphorus because you can generate ligands for transition metals. It turns out that amines are good Lewis bases and they will bind to transition metals, which are typically Lewis acidic. Phosphines are even better, mainly because they're softer. Okay, phosphines still have that lone pair, they still have that Lewis basic character, but the lone pair is in a 3p type orbital instead of a 2p, and that 3p orbital overlaps better with 3d, 4d, and 5d orbitals of the transition metals. So if you take phosphorus trichloride, react it with alcohols, like I said, those PCl3 is very sensitive to water. It's also very sensitive to alcohols. You immediately lose HCl and you generate phosphites. So in this case you have 3 phosphorus oxygen bonds and then whatever R group you want on the phosphine. You can use the same sort of, if you want to call it dehydration chemistry with amines. And so if you throw in 6 equivalents of an amine, at least it has to have at least one NH bond, obviously. You can lose HCl, which is soaked up by the remaining base, and generate phosphenamines. If instead you take the PCl3 and you react it with Grignard reagents, you can make the alkyl and aryl phosphines. And as you might expect, those are going to be stronger Lewis bases than the phosphites because the oxygen is very electron withdrawing. However, a lot of these phosphenamines are very Lewis basic because the nitrogen is donating to the phosphorus and the phosphorus has its own lone pair, and so they can make pretty interesting ligands for transition metals. PCl5 is also a good starting material. Again, you have these main group chloride bonds. They're very reactive. In this case, if you take PCl5 and react it carefully with one equivalent of a primary amine, you can make the phosphorimide. Again, nifty organic transformation. You can take the phosphorimide, and if you react it with a ketone, you can do the azavidig type reaction where now you make the imine instead of the ketone. And that reaction is driven by the formation of the phosphorus oxygen double bond. Phosphorus is very, very oxophilic, so these are often high driving force reactions. Okay. Again, we're kind of blazing through all of the main group elements in 3 lectures, okay? There's a lot of chemistry out there. Even your book only barely scratches the surface on it, especially all of the industrial and real-world applications. So I encourage you to read what's in the textbook, not just assume that the very little that we're covering here in lecture in any way represents the chemistry of the main group elements, other than to be the briefest of introductions. So oxygen. You just can't live without it. I don't know what else to say, right? Oxygen is really funny. So obviously we can't live without it. Every time we breathe oxygen in, we're breathing it in to set off little combustion reactions in our body, okay? That's what respiration is it's a controlled combustion reaction where your body is burning fuel in the presence of oxygen to have energy, to move around, to think, to do whatever you do on a day-to-day basis. What's kind of interesting to me about oxygen is how unreactive it is. Now, you think, well, wait, oxygen reacts with lots of stuff. Lots of stuff burns in oxygen. What do I mean by it being unreactive? Well, what I mean is if you look at the thermodynamics for the reaction of oxygen with a lot of different substrates, you have to pause and wonder why we don't all spontaneously combust. Right? You can have I could have a cup full of gasoline here, exposed to the air, and we could wait forever, right? The gasoline would evaporate before it would react with the oxygen, even though we all know that once that reaction starts, it's incredibly exothermic, right? It's the reaction that powers our car, right? If you have a 4,000-pound car and you're moving it by burning gasoline, well, clearly there's a lot of energy coming out of that. And I know we learn in freshman chemistry, well, kinetics, thermodynamics, they're 2 totally separate things, right? Well, fine. That's kind of lame. It's also not true, but we won't open that can of worms yet. But so what's the deal with oxygen? Okay, why is there such a discrepancy between the thermodynamics of oxygen reactivity and the kinetics? Turns out it's all about spin. So, perfect example. If you take butadiene, again, I could have a cup of it here. It would stink. But oxygen in the air is in its triplet state. Remember, we went through in the MO picture and we proved that oxygen should have 2 electrons in pi star orbitals. And by Hund's rule, we know that they would both go in spin up. We call that a triplet state. That's the whole reason that oxygen is not more kinetically reactive than, or is kinetic. That's why it's kinetically unreactive when thermodynamically it should be exceptionally reactive. We can prove that by converting the triplet state of oxygen, where the electrons in the pi star orbitals are both spin up, and get the oxygen molecule to absorb a photon of energy. And by a photon, I mean 1200 nanometers, which is just infrared. Very low energy light. All it does is take this triplet configuration and flip the spin. Turns 1 electron over so that we now have a singlet. In the case of the butadiene reaction, it immediately does a 1,4 addition. Okay, and we'll go on past that, right? If you generate singlet oxygen, if we lived in a world of, we wouldn't live in a world of singlet oxygen. We would all be running around like, on fire, and not in a good way, right? Instantly, we would all spontaneously combust because we would take away the barrier to the reaction between oxygen and the hydrocarbons in our body. So that's the essence of the kinetic barrier for O2. If you want to get into the quantum mechanics of it, it's a lot of fun. But instead what we'll do is we'll look at the thermodynamics and again drive home this point that from a thermodynamic perspective, oxygen is a powerful reagent. And so we take O2 plus 4 protons plus 4 electrons, that makes water. The electrochemical potential for that reaction is plus 1.23 volts. I'll remind you or tell you for the first time in case you haven't seen the relationship between an electrochemical potential and free energy. That free energy is minus NFE, where E is the potential of the reaction, N is the number of electrons being transferred. So in this case, it's 4. And then F is Faraday's constant, which you can look up in your PChem textbook or many other textbooks. The negative sign there tells you that when you have a chemical reaction that has a positive potential, then that means delta G is very negative in this case. Again, we all know that that reaction is downhill because what is it? Oxygen plus 4 protons plus 4 electrons. How else do we know that reaction? Well, what happens if you take 4 protons and react them with 4 electrons? What do you make? Hydrogen. That's the Hindenburg right there. Okay? Anytime you see one of these nifty cars going around campus that are being developed in the engineering, right? Fuel cell cars, that's the reaction. A fuel cell works on the principle that you can take oxygen from the atmosphere and hydrogen gas. You split the hydrogen into protons and electrons. As they react, the electrons actually go through a circuit. You have electricity. Okay? If you want to get even more reactivity, one way, of course, is to have singlet oxygen. The other is to make ozone. Okay, we all know about the ozone layer up in the top of our atmosphere here. That's why Sherry Rowland got the Nobel Prize here at UCI. Okay, but ozone is an even more powerful oxidant from an electrochemical standpoint. So if you take ozone plus 2 protons plus 2 electrons, you make 1 equivalent of water plus O2. Obviously, that O2 is still reactive. But in this case, the potential is just over 2 volts. So it gives off a lot of energy. Ozone is a very potent oxidant, which is why it's up there in the atmosphere and why it's such a problem to have halogens and freons going up and destroying the ozone layer, or why it was. So the reaction of oxygen to give water seems like a complicated reaction. You need 4 protons, 4 electrons. What about stopping halfway? If you were to react oxygen with just 1 equivalent of hydrogen, you should get hydrogen peroxide, which we all know, right? We have hydrogen peroxide in our medicine cabinet. It's a great way to disinfect cuts. It's kind of cool. You pour it in your cut and it bubbles up and it burns. Ouch. So do you think that's the way that we make it? Turns out that it isn't. Because of the next reaction, hydrogen peroxide plus 2 more protons plus 2 electrons is downhill to give water by 1.76 volts. So we can think about it as we go from oxygen to water. It turns out that you gain a little bit of energy by going to hydrogen peroxide and a lot of energy going hydrogen peroxide to all the way down to water. Actually, I take that back. It's actually, yeah. So what happens is you basically can't stop the reaction at hydrogen peroxide, so you have to get creative. And I love this way that people got creative to make hydrogen peroxide. You use anthraquinone and the anthrohydroquinone with oxygen. And so if you make this hydroquinone, parahydroquinone of anthracene, it will react with O2. The O2 will take it up to the quinone and generate hydrogen peroxide. And because this is already oxidized, the hydrogen peroxide can't do anything further to it. You separate out the hydrogen peroxide and then do a simple hydrogenation reaction. Take this anthraquinone, reduce it with palladium on carbon in the presence of H2, and then you get back to the hydroquinone and you have your catalytic cycle, though it's done in steps, to generate hydrogen peroxide on a large scale. See, organic chemistry is useful for some things. Okay, yeah.
On that last slide, it shows that going from O2 with 4 equivalents of proton, it shows 1.23 volts. And then in the next one with hydrogen peroxide, with the same reactance of an O2 molecule and 4 protons, you combine those two, it's overall, I think, 2.46 volts. Why the discrepancy?
Because the reactions don't balance out exactly, right? Because if you go, what did I do here?
I guess because the top reaction is maybe half of the energy gained by the bottom reaction?
Well, so hang on, let me see, what did I do here? 2 protons, 2 electrons. I actually think the problem is I'll have to get back to you. I'm not sure what the issue is right there. But you're right. They should, those two reactions should add up so that they have the same potential as the 1.23. I will have to get back to you. Good catch, though. Okay, so the oxides. A complex, we call a complex an oxide as long as it has oxygen in the 2- oxidation state. So this is not formal charge as long as the oxidation state of the oxygen atom is 2-. So technically, okay, technically you would say a ketone is an oxide, right? Because oxygen is more electronegative than carbon, and so those electrons should go to the oxygen, and it would technically be an oxide by that definition. Obviously, we don't generally apply that nomenclature to things like ketones or alcohols or anything like that, unless the alcohol is bound to a transition metal. So if you take calcium oxide and react, we have the basic oxides. There we have calcium bound to a transition metal. It's formally 2-. Obviously, this is a fairly ionic interaction. But this is known as a basic oxide because when you take calcium oxide, put it in water, you generate calcium hydroxide. So if you think about it now, what you have is a source of hydroxide, okay, which is going to make the solution more basic. Similarly, with magnesium oxide, it will take up 2 protons and generate the magnesium dianion and water. Okay, so in both of these reactions, you're either generating a hydroxide-like species in solution or you're soaking up protons in the solution. Either way, what you end up with is a more basic solution, and so those types of compounds are termed the basic oxides. And as you might expect, it's mostly the metals in the alkali and alkaline earth columns. There are also acidic oxides. These generally are going to be oxides of the P block elements. And so N2O5, if we put that in water, it generates 2 equivalents of nitric acid. Okay, immediately by dissolving N2O5 in water, the solution becomes more acidic because we produce nitric acid. Same thing in this case, if we take this antimony oxide, it's going to soak up hydroxide in water to generate the antimony hexahydroxide anion. If we're soaking up hydroxide, that's going to generate more free protons in solution, and the solution is going to be acidic. Finally, this is really a Goldilocks effect, and the amphoteric oxides are the ones that are right in the middle. And so things like zinc oxide can either act as basic or as an acidic oxide. And so in acid solutions, zinc oxide will soak up protons to generate the zinc dication in water. Alternatively, if you take zinc oxide and you put it into a basic solution, it'll soak up the base and generate zinc tetrahydroxide, effectively neutralizing the basic solution. So an amphoteric oxide like this, you could think of it almost acts as its own buffer. Okay, it can react with acids or it can react with bases, depending on which is in excess in the aqueous solution. Okay. Real quickly, one more slide. Well, no, we'll stop here for today, and then we'll blow through the rest of this on Wednesday. Have a great afternoon.